Welcome to Monday afternoon physics with an unorganized university student. This week's quote of the week goes to Arthur C. Clarke, who said, "Any sufficiently advanced technology is indistinguishable from magic." The aim of this week's laboratory was to measure the amount of magnetic force one dipole biomagnet applies to another. The items we were given to do so were multiple weighted balls, a long cylindrical hollow tube, a magnet, a stand, and a clamp. Initially, we were very confused. We believed that to measure the magnetic force, we required a source of charge. Obviously, we were wrong, and a deeper understanding of magnets was required. And so we went out and researched the basics, and from those basics, we built. To understand why a force is present, we must first comprehend the wonder of magnets. To surmise, every magnet has a north pole and a south pole. From the picture displayed to the left, we see that the like poles repel each other and the opposite poles attract each other. The direction of the arrows should also be noted, that being from north to south. This attraction is due to the movement or flow of electrons from the north pole to the south pole. We were then faced with two choices. We could measure the force of attraction or the force of repulsion. We chose to determine the force of repulsion because we intuitively thought that this would be marginally easier than determining the force of attraction. By understanding the magnetic poles and the flow of electrons, we set up the experiment, which is shown to the right. The experiment involved calculating the force present by multiplying the gravitational constant and the collective weight of one magnet plus the weighted balls. We also measured the distance between both the magnets every time we added a ball. The table below displays the results we gained from conducting the experiment. However, it should be noted that as we repeated the same step 60 times, and as humans crave new experiences to feel stimulated, the likelihood of an error is very large, especially as we began rushing the measurements beyond the 12th-ish ball. As such, uncertainty must be taken into account, and therefore the measured distance is plus or minus 5 millimeters. From knowing that we use two dipole bar magnets as well as the force, we can use basic algebra to find the magnetic force of repulsion. The distance has a power to 4 due to the presence of two dipole bar magnets. The rest of the math you can read at your leisure, as it would be easy to follow as opposed to me just spouting endless letters and numbers at you. However, the line graph translates information from the previous slides, implementing the algebraic formula deduced, giving an easy and informative graph, and I would recommend looking at that as opposed to the math. The experiment involved using the force calculated by multiplying the gravitational constant with the mass. From this, we can rearrange the equation to interpret the magnetic force between the two bar magnets. By doing so, we can accurately measure the repulsive force and thus the net magnetic force observed between the two. In truth, the phenomenon of magnetism is more perplexing than how I always seem to be the person to draw the fourth king in King's Cup. However, this lab has increased my knowledge of the field. Get it? Of the field? Nah, no takers? Okay, moving on. But by no means does that translate to a deep understanding. I will definitely delve further into this area, as anything complex is always a good distraction.